a quiet archive record. Tonight, we step into the stillness between moments, where thoughts dim and the mind begins to wander. This documentary episode follows a single question taken to an extreme. What happens when you zoom in forever? We start at a familiar human scale and move down in clear steps, each one shrinking the view and changing what the world looks like. Along the way, we cross the borders between biology and chemistry, between chemistry and atomic physics, and then into the strange rules of quantum fields. At every checkpoint, we describe what is visible, what is real at that scale, and what numbers begin to dominate, like temperatures, time scales, and the speed of the motion inside matter. The goal is not to overload you with math. The goal is to build a clean mental picture of the smallest named layers we can talk about, and to end at the edge where our current physics stops giving confident answers. Tonight, we zoom in forever. Checkpoint 1, 1 meter. Start with the size of a yardstick. At this scale, objects look solid and continuous. A tabletop is a flat surface. A fingertip is smooth. Air seems empty. Temperature is something you feel as a single number. Time is the steady beat of seconds. But even here, the world is already moving. The atoms in a solid are vibrating. In a warm room, each atom in a table is jittering around its position. It is not sliding across the table. It is shaking in place, billions of times per second. That microscopic motion is what we call heat. Checkpoint 2, 10 centimeters. Now you are close enough to see texture. Skin is not smooth. Wood grain becomes a landscape. Dust is not a vague idea. It is visible as tiny grains and fibers. The air is also not empty. It carries water vapor, nitrogen, oxygen, and floating particles. A room is full of motion. Molecules are colliding in every direction. Even in still air, the average speed of an air molecule at room temperature is on the order of hundreds of meters per second. The reason you do not feel a wind is that their directions are random and balanced. Checkpoint 3, 1 centimeter. This is the scale of a fingernail. You can see pores and hairs. You can see cracks in paint. You can see the tiny hills of fabric weave. Here, biology is still visible as shape. Cells are still too small to see with the naked eye, but life leaves clues. Skin oil shines. Tiny droplets form. Bacteria are present but invisible. Checkpoint 4, 1 millimeter. Now you are at the scale of a grain of sand. You can see the jagged edges of dust. You can see the blunt ends of a hair. If you could watch a living surface at this scale over time, you would see slow changes. Sweat beads form. A droplet evaporates. A small insect crosses the field. Checkpoint 5, 100 micrometers. A micrometer is a millionth of a meter. 100 micrometers is a tenth of a millimeter. This is around the thickness of a human hair. A hair is not a simple cylinder. Its surface has overlapping scales like roof shingles. Dust sticks in grooves. Oils and water cling. The world begins to look like a rugged canyon system. Checkpoint 6, 50 micrometers. Now you approach the size of many single cells. Some large cells, like certain eggs, are bigger. Many bacteria are smaller. But this is the doorway where biology becomes a landscape of units. At this scale, liquid water is thick. Surface tension matters. A tiny droplet behaves like a stretchy skin. Viscosity dominates. Things do not splash the way they do at human scale. Checkpoint 7, 20 micrometers. This is the scale of many human cells. A red blood cell is about 7 to 8 micrometers across, so we are still slightly larger than that. But now a cell is not a point. It is an object. If you could see a cluster of cells, you would see membranes, soft walls, and internal structures. The motion you would notice is slow and purposeful. Cells drift, squeeze, and flow, pushed by forces that feel like gentle pressure at this scale, but are enough to rearrange tissue. Checkpoint 8. 10 micrometers. Now you can see the size of a typical cell clearly. A cell is a sack of water packed with machinery. It is not empty fluid, it is crowded. Inside, the temperature is the same as the body, around 37 C in a human. But at this scale, temperature is not a smooth glow. It is the statistical motion of molecules. The machinery works because molecules are constantly bumping. Checkpoint 9. 5 micrometers. You are now at the scale of bacteria on the large side and organelles inside cells. A mitochondrion is often around 1 micrometer, so you are still larger, but you can imagine it. The strange thing here is that random motion becomes a driving force. Brownian motion, the jiggling caused by molecular impacts, is not a curiosity. It is a constant storm. Molecules never sit still. Checkpoint 10. 1 micrometer. Now you are at the scale of bacteria, mitochondria, and tiny structures inside cells. A bacterium is a small chemical factory. It has no internal organs in the same way our cells do, but it still has membranes, genetic material, and ribosomes. It lives in a world where water feels syrupy and where gravity is weak compared to surface forces. Checkpoint 11. 500 nanometers. A nanometer is a billionth of a meter. 500 nanometers is half a micrometer. Now you are in the range of large viruses and the smallest bacteria. A virus is not alive in the full cellular sense, but it is a package of instructions and tools. It is a molecular machine wrapped in protein. At this scale, the idea of a rigid surface becomes fuzzy. Proteins fold and flex. Their shapes are stable on average, but they vibrate. Checkpoint 12. 200 nanometers. Many viruses fit here. A virus at this size can be a spiky sphere or a complex capsule. The important fact is that what you call a shape is an energy minimum. A protein shell holds its form because that arrangement is stable. Heat shakes it, but the structure stays because chemistry is a set of bonds and forces. Checkpoint 13. 100 nanometers. This is the scale of large protein complexes and small viruses. If you zoom in on a membrane at this scale, it is a sea of molecules. It is a lipid bilayer with proteins floating inside it. It looks like a moving mosaic. The parts slide sideways. The membrane is more like a fluid than a wall. Checkpoint 14. 50 nanometers. Now you are in the range of ribosomes, the machines that build proteins. A ribosome reads genetic code and links amino acids into a chain. That chain folds into a protein. The speed is not human fast, but it is not slow either. A cell can build many proteins per second across many ribosomes. Checkpoint 15. 20 nanometers. This is the scale of many individual proteins. A protein is not a static sculpture. It is a dynamic object vibrating at room or body temperature. It flexes, twists, and breathes. The function of a protein often depends on its ability to change shape. Checkpoint 16. 10 nanometers. At this point, a protein is a large object. DNA is also visible as a thick rope. DNA is about 2 nanometers wide, but in a cell, it is wrapped, packed, and organized. At 10 nanometers, you can see the first level of packing, where DNA wraps around proteins called histones, forming bead-like units. Checkpoint 17. 5 nanometers. Now you are near the width of a small protein. and only a few times larger than the width of DNA. Water is everywhere, but water is not a smooth background. It is a crowd of individual molecules. Each water molecule is polar. It has a positive side and a negative side, and that polarity creates strong local forces. Checkpoint 18, 2 nanometers. Now you can see DNA as a double helix with a real thickness. You can see the grooves where proteins bind. At this scale, chemistry is no longer an abstract subject. It is geometry. Bonds form because electrons arrange themselves into stable patterns. The shapes of molecules matter. Checkpoint 19. 1 nanometer. This is the scale of small molecules like sugars, amino acids, and many drug molecules. A single nanometer is also a scale where quantum effects are not optional. Electrons in molecules occupy quantum states. They are not tiny planets orbiting a nucleus. They are probability clouds. Checkpoint 20. 5 angstroms. An angstrom is 0.1 nanometers. 5 angstroms is half a nanometer. This is the scale of individual chemical bonds. A carbon-carbon bond length is around 1.5 angstroms. The distance between atoms in a molecule is a few angstroms. At this scale, you do not see solid spheres. You see electron clouds overlapping. A bond is not a rod. It is a shared set of electrons in a stable arrangement. Checkpoint 21. 1 angstrom. Now you are at the size of a single atom. The typical size of an atom is around 1 angstrom to a few angstroms depending on how you define size. An atom is mostly empty space. The nucleus is tiny compared to the overall electron cloud. If the atom were a stadium, the nucleus would be a speck near the center. But empty space here does not mean nothing. It means fields. The electron cloud is a quantum field pattern. Checkpoint 22. 50 picometers. A picometer is a trillionth of a meter. 50 picometers is half an angstrom. Now you are shrinking into the deep interior of the atom. The electron cloud is still what defines size. You are moving toward the nucleus. The energy scales rise. To probe smaller distances, you need higher momentum, which in practice means higher energy particles. Checkpoint 23. 10 picometers. At 10 picometers, you are still outside the nucleus, but you are far inside what most people imagine as the atom. If you had a beam of electrons or X-rays probing distances like this, you could begin to see the arrangement of inner electron shells. Checkpoint 24. 1 picometer. Now you are 1,000 times smaller than an atom. At this scale, the nucleus is no longer a point. It becomes the target. Chemistry is gone. The rules now are nuclear physics and particle physics. Checkpoint 25. 100 femtometers. A femtometer is 10 to the minus 15 meters. 100 femtometers is still larger than a nucleus, but close. A typical atomic nucleus is a few femtometers across. So at 100 femtometers, you are watching a region where the strong nuclear force will start to dominate. Checkpoint 26. 10 femtometers. Now you are in the rough size range of a small nucleus. The nucleus is not a hard ball. It is a quantum system of protons and neutrons bound together by the strong force. The energies are extreme compared to chemistry. Binding energies are in millions of electron volts, not a few electron volts. Checkpoint 27. 5 femtometers. At this point, a single nucleus fills your view. If you could freeze time and look, you would not see protons and neutrons sitting still. You would see a fuzzy quantum object. The nucleons have wave-like behavior inside the nucleus. Checkpoint 28. 2 femtometers. Now you are at the scale of a single proton. A proton is not elementary in the way an electron is. It is made of quarks and gluons. But you do not see quarks as little beads. You see a storm of quantum fields. Quarks are confined. They cannot be pulled out as isolated objects under normal conditions. Checkpoint 29. 1 femtometer. This is a classic proton-size scale. Here, the strong force is overwhelming. Gluons carry the force that binds quarks. The energy inside a proton is huge. Most of the proton mass is not in the quarks themselves, but in the energy of the fields and the motion. Checkpoint 30. Half a femtometer. Now you push deeper into the proton. The inside is not a simple 3-quark picture. There are C-quarks and gluons popping in and out. This is quantum chromodynamics, a theory that is very successful but difficult to visualize. Checkpoint 31. 1/10 of a femtometer. At this scale, you are probing very high energies. One way to think about it is that distance and energy are linked. To see smaller distances, you need shorter wavelength probes, which means higher energy. In particle accelerators, this corresponds to collisions at enormous energies. The results are showers of particles. Checkpoint 32. 100 atometers. An atometer is 10 to the minus 18 meters. 100 atometers is 10 to the minus 16 meters. Now you are in a region where the electroweak scale begins to matter. The forces we treat separately at low energy start to look like they belong to a unified framework. Checkpoint 33. 10 atometers. At this scale, you are far below the size of a proton. Particles like electrons and quarks behave like point particles in experiments down to very small distances. That does not mean they are truly points. It means we have not detected a size. Checkpoint 34. 1 atometer. Now you are at 10 to the minus 18 meters. If you could probe at this scale, you should be looking for new physics. You might find evidence of extra dimensions, compositeness, or new particles. But in our current experiments, we have not found clear signs. The standard model keeps working. Checkpoint 35. 1 zeptometer. A zeptometer is 10 to the minus 21 meters. This is so small that our everyday intuition fails completely. At these scales, the idea of a particle traveling on a path is not useful. Instead, physics is best described as interactions of quantum fields. Checkpoint 36. 1 yoctometer. A yoctometer is 10 to the minus 24 meters. Now you are approaching a region where energies would be far beyond what we can produce on Earth. Even cosmic rays do not routinely probe the extreme end of this range in a controlled way. Checkpoint 37. The electron-Compton wavelength scale. There is a special scale associated with each particle called a Compton wavelength. For an electron, it is about 2.4 picometers. This is not a size in the simple sense. It is a scale where quantum field effects become important, like particle creation in high-energy interactions. It reminds you that the vacuum is not empty. Under the right conditions, energy can turn into particle pairs. Checkpoint 38. The vacuum at small scales. As you zoom in further, you might expect to see emptiness between particles. Instead, quantum field theory suggests the vacuum has fluctuations. Fields have a ground state, and even in that ground state, there is structure. It is not a foam you can see directly, but it affects measurable things like the Casimir effect. Checkpoint 39. Time scales begin to shrink. At human scale, a second is a meaningful unit. At atomic scales, typical vibration times are around 1/trillionth of a second or less. At nuclear scales, interactions can involve times around 10 to the minus 22 seconds. As you zoom in, the relevant time scales shrink with the relevant energies. Fast becomes the default. Checkpoint 40. Temperature is kinetic energy. At the start, temperature felt like a room number. Here it is clearer. Temperature is a way to describe the average energy of random motion. In a solid at room temperature, atoms vibrate with energies around a fraction of an electron volt. In a star core, temperatures reach millions of degrees and particles move much faster. At particle physics scales, the equivalent temperatures can be billions or trillions of degrees in the early universe. Checkpoint 41. The early universe as a zoom reference. One way to picture extreme energies is to look backward in time. As the universe was younger, it was hotter and denser. At very early times, energies were so high that the distinctions between particles and forces look different. So zooming in is connected to the first fractions of a second after the Big Bang. Checkpoint 42. The electroweak scale. Around energies of about 100 billion electron volts, the electromagnetic force and the weak force are described together as the electroweak interaction. At lower energies, they appear different. At higher energies, their symmetry becomes visible. This is a real example of zooming in, revealing hidden unity. Checkpoint 43. Quark-gluon plasma. If you heat matter to extreme temperatures, like those in heavy ion collisions, protons and neutrons can melt into a quark-gluon plasma. This is not a theory only. It has been created in laboratories for tiny moments. It is a state of matter where quarks and gluons are not confined into individual protons and neutrons. Checkpoint 44. The scale where gravity still seems weak. Even as you zoom into particles, gravity is strangely weak compared to other forces. The gravitational attraction between two protons is absurdly small compared to their electric repulsion. This mismatch is one of the deep puzzles. It suggests that our understanding of gravity is incomplete at small scales. Checkpoint 45. The Planck length approaches. The Planck length is around 1.6 times 10 to the minus 35 meters. This is not just a random number. It is built from fundamental constants: the speed of light, the gravitational constant, and Planck's constant. It is the scale where our current theories begin to clash. Quantum mechanics and general relativity both matter, and they do not fit neatly together. Checkpoint 46. The Planck time. The Planck time is about 5.4 times 10 to the minus 44 seconds. This is an unbelievably short time. It is sometimes described as the smallest meaningful timescale, but that is not certain. It is a sign that below this time, our equations may stop being reliable. Checkpoint 47. What does space mean here? At familiar scales, space is a smooth stage. Near the Planck length, some theories suggest space could be quantized. It could have a discrete structure. Other theories suggest space remains continuous, but that our measurements become impossible because probes would create black holes. So the barrier might be physical, not just technical. Checkpoint 48. The black hole limit idea. If you try to localize energy into a tiny region, you can form a black hole. This means that at extreme zoom, the act of looking can change the thing you want to see. It is like a cosmic microscope that breaks the sample. Checkpoint 49. Strings, loops, and other possibilities. Some proposed theories, like string theory, suggest that the smallest objects are not points, but extended strings. Other approaches, like loop quantum gravity, suggest that space-time itself has discrete loops or networks. There is no final proof yet, but the common theme is that zoom in forever may not reveal smaller and smaller classical objects. It may reveal that the idea of smaller breaks. Checkpoint 50. The smallest named thing we can talk about with any confidence. In practical terms, the smallest named scale that shows up again and again is the Planck scale. Below it, we can write speculation, but we cannot yet test it. So the final view is a border. It is the border where the words particle and space and time might be the wrong words. It is the border where reality might be described as information, geometry, or something we have not named. And it is the border that reminds you that zooming in is not only about size, it is about the rules changing as you cross thresholds, from the cell to the molecule, from the molecule to the atom, from the atom to the nucleus, from the nucleus to the quark and the field, and then to the point where the map we use ends. If you return to the human scale after this journey, the world looks the same. The table is still there. The air still feels empty. But you now carry a second picture. A picture of a world made of motion. A picture of emptiness that is not empty. And a picture of the smallest named boundary we can reach with our current understanding. To make this journey more vivid, we can slow down and add depth to the checkpoints that mark real changes in the rules. Checkpoint 51. What you are really zooming through. When you zoom in with a camera, you are just magnifying light that bounced off a surface. When you zoom in with a microscope, you often do not use ordinary light at all. You use electrons, or X-rays, or scanning probes. So in this thought experiment, the zoom is not only optical, it is conceptual. It is a promise that at each step, you have a tool that can resolve that scale without destroying it. In reality, that promise breaks in places. The reason it breaks is that to see smaller, you need higher energy probes. Higher energy probes can heat, ionize, or break the system you are studying. So the deeper you go, the more your method becomes part of the story. Checkpoint 52. The world of thermal motion. Back near human scale, you can ignore the jitter in solids. But at the scale of atoms, thermal motion is not background. It is the main motion. In a solid, atoms sit in a lattice. They are held by electric forces in a repeating pattern, but they are never fixed. At room temperature, atoms vibrate around their positions. Those vibrations come in quantized packets called phonons. This means that even sound inside a crystal is a quantum phenomenon. Heat moves through a solid partly as these quantized vibrations. Checkpoint 53. Why solids feel solid. At first glance, a solid seems like a dense block of matter. But the spacing between atoms in a solid is mostly empty compared to the size of the nucleus. Solidity comes from electromagnetic forces and from the quantum rules that prevent electrons from all falling into the same state. The Pauli exclusion principle, a quantum rule for fermions like electrons, is one of the reasons matter has volume. So when you press your hand on a table, you are pushing against fields and quantum rules, not against little marble atoms. Checkpoint 54. The chemistry threshold. There is a scale where the word chemistry stops being the right word. As long as you care about how atoms share electrons, you are doing chemistry. As soon as you care about the nucleus, you are doing nuclear physics. That border is not vague. Chemical energies are in electron volts. Nuclear energies are in millions of electron volts. 1,000,000 to 1 jump. That is why chemical reactions can be reversed and controlled in a lab, while nuclear reactions release enormous energy and can change one element into another. Checkpoint 55. The nucleus is not tiny planets. When people first learn atoms, they sometimes imagine a nucleus with electrons orbiting like planets. That picture is useful only as a cartoon. In reality, both electrons and nucleons are quantum objects. They have wave functions. They have uncertainty. They do not have precise little orbits. So at this point, zooming in is not like getting closer to a statue. It is like getting closer to a fog that has structure. Checkpoint 56. The strong force is strange. The strong force does not behave like gravity or electricity. In gravity and electricity, forces weaken with distance. In the strong force, the story is different. At the scale of a proton, the force between quarks becomes weaker when they are extremely close. This is called asymptotic freedom. But when you try to separate quarks, the force does not fade away. It becomes stronger, so you cannot pull a quark out the way you could pull a charged bead away from another bead. The energy you put in turns into new particles. This is a mind-bending rule change. Checkpoint 57. Mass is not just stuff. When you hold a proton in your mind, it feels like a tiny chunk of matter. But if you ask where its mass comes from, you find something surprising. The quarks inside a proton have some mass. But most of the proton mass comes from energy. It comes from the motion of quarks, and from the energy stored in gluon fields. So the mass of ordinary matter is mostly trapped energy. This is not poetry. It is measured. Checkpoint 58. The vacuum is an active stage. As you zoom down to particle scales, the vacuum starts to matter. In classical physics, a vacuum is just empty space. In quantum field theory, each field has a lowest energy state. Even in that lowest state, there are fluctuations. Those fluctuations can show up as real effects. For example, two uncharged metal plates placed very close together experience a tiny attraction due to changes in vacuum fluctuations between them. This is the Casimir effect. So the idea of nothing becomes unstable. Checkpoint 59. What you mean by a particle? At a human scale, an object is a thing with a position. At quantum scales, a particle is often the smallest unit of an interaction. It can be described as an excitation of a field. An electron is an excitation of the electron field. A photon is an excitation of the electromagnetic field. So when you zoom in and ask, where is the electron? The most honest answer is that the electron is spread out until an interaction localizes it. Checkpoint 60. Measurement becomes an event. At very small scales, you do not passively observe, you interact. A measurement is a collision, a scattering, an absorption. The thing you learn comes from what happens when the system and the probe exchange momentum and energy. So the zoom is not a gentle look, it is an event. Checkpoint 61. A different kind of image. At the level of atoms, a true image is often not a photograph. A scanning tunneling microscope, for example, builds an image by scanning a needle tip over a surface and measuring a quantum tunneling current. The result is a map of electron density. So the picture at this scale is a plot of probabilities, not a direct snapshot. Checkpoint 62. The speed inside matter. Earlier we said air molecules move at hundreds of meters per second. Inside a solid, the electrons that form bonds also have motion, and the typical speeds can be a significant fraction of the speed of light in heavy atoms. Even in lighter atoms, electron motion is fast. This does not mean electrons are little balls whipping around. It means their quantum states have high momentum components. So the interior of matter is a fast world masked by stability. Checkpoint 63. Time at the atomic scale. If you look at how fast atoms vibrate in a solid, the frequency can be in the terahertz range, trillions of cycles per second. That means a single vibration period can be a picosecond, a trillionth of a second. So in the time it takes you to blink, atoms have completed trillions of oscillations. Checkpoint 64. Temperature as a scale marker. A useful fact in physics is that temperature can be converted to energy. Room temperature, around 300 Kelvin, corresponds to about 0.006 electron volts of thermal energy per degree of freedom. That is small compared to chemical bonds, which are a few electron volts. That is why molecules can stay intact at room temperature. But in a very hot plasma, thermal energies can exceed bond energies, and matter becomes ionized. Checkpoint 65. Ionization is a threshold. If you heat a gas enough, atoms lose electrons. Then you have a plasma. A plasma is not a rare thing. It is the most common state of visible matter in the universe. Stars are plasma. Lightning is plasma. Some neon signs are plasma. So as you zoom out, most of the universe is not solids and liquids like on Earth. It is hot ionized gas. Checkpoint 66. The scale of light itself. Visible light has wavelengths from about 400 to 700 nanometers. That means visible light cannot directly resolve objects much smaller than a few hundred nanometers. This is why ordinary microscopes have a limit. To see smaller, you need shorter wavelengths, like ultraviolet, X-rays, or electron beams. So the zoom is tied to the wavelength of your probe. Checkpoint 67. The quantum of action. Planck's constant sets the scale where quantum effects matter. It is not because the world is small. It is because action, the product of energy and time, comes in chunks when it is comparable to Planck's constant. This is why tiny systems show quantization, and it is why large systems can look continuous. Checkpoint 68. The particle zoo is not just decoration. When you collide particles at high energy, you create new particles. Some of them live for fractions of a second. Some live for trillionths of a second. Some decay in 10 to the minus 25 seconds. These particles are not meaningless. They reveal the symmetries of the underlying fields. In that sense, zooming in is like breaking matter into its language. Checkpoint 69. The idea of a field is the deeper layer. At human scale, we talk about objects. At deep scale, the most stable description is fields. Fields fill space. They can store energy. They can vibrate. They can interact. Particles are like the notes. The field is like the instrument. Checkpoint 70. The edge where gravity must join the story. As you go far beyond the scales we can test, gravity should stop being a background. At small enough distances and high enough energies, quantum effects of gravity should appear. The Planck scale is where that is expected. We cannot reach it in experiments with current technology, but nature reached it in the early universe. So our best clue comes from cosmology. Checkpoint 71. The early universe timeline. At about 1 second after the Big Bang, the temperature was around 10 billion Kelvin. That is a temperature where nuclei can form. Earlier than that, matter was a hot plasma of particles. Earlier still, it may have been a phase where the electroweak symmetry was unbroken. And earlier than that, at the Planck time, our known equations do not reliably apply. This is the zoom in forever story, written as a time story. Checkpoint 72. Why we do not know the smallest thing. It is tempting to say there is a smallest possible thing, like a final pixel. But physics does not yet confirm that. It offers hints. It offers scales where our tools fail. It offers theoretical frameworks. but it does not yet offer a measured smallest object. What we have is a frontier. Checkpoint 73. What is mind-blowing about the frontier? The mind-blowing part is not only the smallness, it is the idea that the concepts you rely on can break. Space might not be smooth, time might not be fundamental, particles might not be basic, even cause and effect might need a deeper description. Checkpoint 74. A final loop back to the start. If you zoom back out, you return to the familiar. But now you can see that the familiar is a summary. A table is a summary of fields and electrons and vibrations. Air is a summary of collisions and random motion. A warm room is a summary of trillions of invisible impacts. So the zoom in Forever story is also a story about how the large world is built from averages. Checkpoint 75. The last named scale, stated plainly. If you ask for the smallest possible thing we can name with confidence, we can name the Planck scale. We can name quarks and electrons and photons. We can name nuclei and atoms and molecules. We can name the distances and energies where our theories work, and then we can name the border. After that border, we can offer possible maps, but we cannot yet say what is truly there. That is where this zoom ends. We can add more checkpoints to reach the smallest named ideas more carefully, and to make the middle layers more informative. Checkpoint 76. The scale of a human hair revisited. At around 70 micrometers, a hair is wide enough to cast a strong shadow in microscope light, but it is also wide enough to show a key theme of small scales. At large scale, a hair is a dead fiber. At small scale, it is a layered composite. It has a cuticle, a cortex, and sometimes a central medulla. It is built from keratin proteins, packed and cross-linked. So even something simple is a hierarchy. Checkpoint 77. The world where friction changes. At human scale, friction is a constant you measure. At micro scale, friction is often dominated by surface forces. A gecko can climb glass because of microscopic hairs that increase surface contact. At this scale, van der Waals forces, weak attractions between molecules, can become powerful when many contacts add up. So the rules of grip and stickiness change as you zoom. Checkpoint 78. The scale of bacteria in motion. A bacterium swimming in water does not coast. At micro scale, inertia is tiny compared to viscosity. If a bacterium stops pushing with its flagellum, it stops almost immediately. This is the low Reynolds number world. It is like moving through honey. So propulsion is different. You cannot swim by doing a simple back and forth motion, because the fluid just reverses. You need a non-reversible stroke, like a rotating corkscrew. Checkpoint 79. Diffusion dominates. At human scale, you can carry a molecule by blowing air. At microscale, diffusion becomes the default transport method. Diffusion is the random walk of particles. It is slow over long distances, but fast over short ones. A molecule can diffuse across a cell in a fraction of a second, but it can take hours to diffuse across a millimeter. So life at cell scale is built around short distances. Checkpoint 80. The scale of viruses and the idea of a template. A virus is a template that hijacks a cell. Its physics is chemistry and mechanics. The capsid is a shell that can be strong and springy. Some viruses inject genetic material like a loaded syringe, driven by internal pressure. So even at 100 nanometers, you can have pressure, tension, and stored energy. Checkpoint 81. The scale of proteins as machines. A protein like kinesin walks along a microtubule, carrying cargo in a cell. It takes steps, Each step is driven by ATP, a molecule that stores chemical energy. The step size is around 8 nanometers, so you can talk about a walking machine that is smaller than a virus. That is one of the sharpest mind blows in biology. Checkpoint 82. The temperature inside molecules. At room temperature, molecules are vibrating. They have rotational and vibrational modes. These modes are quantized. That means molecules have discrete energy levels. Infrared light can excite specific vibrations. So at this scale, temperature and light and chemistry merge. Checkpoint 83. The scale of electron orbitals. In an atom, electrons occupy orbitals. An orbital is not a path. It is a shape of probability. The shapes have names like S, P, D, and F. These shapes determine chemical behavior. So chemistry is the shadow of quantum geometry. Checkpoint 84. The scale of atomic spacing. In a solid, atoms are spaced about a few angstroms apart. That spacing is why crystals form regular patterns. It is also why X-ray diffraction works. When X-rays with wavelengths comparable to atomic spacing scatter off a crystal, the waves interfere and create patterns. Those patterns let us infer structure. So the smallest architecture of matter can be read like a code. Checkpoint 85. The nucleus as density. If you could compress matter to nuclear density, you get an astonishing number. A teaspoon of neutron star matter would have a mass comparable to a mountain. That is because the nucleus packs almost all of an atom's mass into a tiny volume. So density is another form of zoom. It shows how much emptiness exists in ordinary matter. Checkpoint 86. Neutron stars as a zoom endpoint in nature. A neutron star is a city-sized object with about the mass of the sun. In its crust and core, matter is in exotic phases. Neutrons dominate. Some models suggest superfluid neutrons and superconducting protons. So nature already explores states that are far from everyday solids. Checkpoint 87. The scale of particle decay. At high energies, unstable particles appear. Their lifetimes tell you about interaction strength. A particle that decays in 10 to the minus 25 seconds interacts very strongly. A particle that decays in microseconds interacts more weakly, so time becomes a way to measure force. Checkpoint 88. The speed limit in every checkpoint. Across all these scales, one number never changes. The speed of light. It is not just the speed of light. It is the speed limit for information. It is also the conversion factor between space and time in relativity. So as you zoom in, you can keep that as an anchor. Nothing in the known universe outruns it. Checkpoint 89. The energy scale ladder. A useful ladder is this. Chemical bonds are a few electron volts. Atomic inner shells can be thousands of electron volts. Nuclear binding energies are millions of electron volts. Particle physics can be billions of electron volts. Cosmic rays can reach far beyond that. The Planck energy is around 10 to the 19 billion electron volts. That is an enormous gap. Checkpoint 90. The Planck energy and why it is unreachable. The Planck energy corresponds to about 2 billion joules. That is the energy of a large truck moving at highway speed, concentrated into a single particle. We cannot do that. Even the most powerful accelerators are far below, so we cannot directly probe the Planck regime. Checkpoint 91. Why gravity becomes a problem. Gravity is weak in everyday particle interactions. But if you concentrate enough energy into a tiny region, gravitational effects become significant. At the Planck scale, the gravitational interaction of a particle with itself is expected to be strong. So the separation between quantum physics and gravity disappears. Checkpoint 92. The idea of space-time foam. Some people describe the Planck regime as space-time foam. This is an image, not a proven fact. It suggests that on extremely small scales, space-time could fluctuate. Distances could be uncertain. Geometry could be dynamic. If true, then the very act of defining a precise distance could fail. Checkpoint 93. Discreteness versus continuity. A key question is whether space-time is continuous or discrete. If it is discrete, there could be a smallest unit, like a pixel. If it is continuous, there is no smallest length, but there may still be a smallest meaningful measurement due to physics limits. Both possibilities keep the Planck scale as a boundary. Checkpoint 94. Extra dimensions. Some theories suggest there could be extra spatial dimensions that are curled up and small. If that were true, then zooming in could reveal new directions of motion. Gravity could appear weak because it spreads into extra dimensions. This is speculative, but it is one of the few ways to explain the weakness of gravity. Checkpoint 95. Unification as a zoom theme. We already saw that electromagnetic and weak forces unify at high energy. Some theories suggest that all forces could unify at even higher energy. If that is true, then zooming in would not only reveal smaller objects, it would reveal simpler underlying rules. Complexity at large scale could come from symmetry, breaking at small scale. Checkpoint 96. Symmetry breaking as a cosmic phase change. In the early universe, as temperature dropped, symmetries broke. This is like a phase change. When water freezes, it breaks symmetry and forms crystals. When the universe cooled, it may have changed phases and produced the forces and particles we see. So zooming in is tied to the universe's history. Checkpoint 97. The smallest thing we can name in the everyday sense. If you want the smallest stable particle in ordinary matter, you can name the electron. You can name photons. You can name neutrinos. But even those are excitations of fields. So the thing is not a bead. It is a rule and a field pattern. Checkpoint 98. The boundary between known and unknown. We can say what we have tested. We can say what we infer. We can say what we guess. The tested region includes atoms, nuclei, and particles of the standard model. The unknown region includes quantum gravity. Between them is a long desert of scale. Checkpoint 99. Why the desert might hide surprises. Even if the standard model works at the energies we have tested, it might not be the final theory. There could be new particles at higher energies. There could be new symmetries. There could be new interactions. There could be dark matter particles that rarely interact with us. So the zoom may still have hidden layers. Checkpoint 100. The reason this is not only about smallness. The deepest point of this journey is that scale changes what is real. At one scale, friction is a surface phenomenon. At another, friction is a story about electron clouds. At one scale, heat is a feeling. At another, heat is quantized vibration. At one scale, mass is weight. At another, mass is field energy. So zooming in forever is a way to see that reality is not one picture. It is many pictures stacked, each with its own rules. And the smallest named place we can point to, for now, is the Planck boundary, where our best maps stop being reliable. Checkpoint 101. A tighter look at a single droplet. At around 1 millimeter, a water droplet is still a droplet. But zoom to tens of micrometers, and you see that a droplet is a curved surface held together by molecular attraction. That surface behaves like a stretched membrane. Tiny insects can stand on it. A needle can pierce it. and the pressure inside depends on curvature. Smaller droplets can have higher internal pressure. This shows that geometry becomes physics as you shrink. Checkpoint 102. The scale of sound in air. Sound is a wave of pressure. At human scale, sound is smooth. At micro scale, sound is still made of molecules colliding. Air at room temperature has a mean free path. The average distance a molecule travels between collisions of around tens of nanometers. That means that below that scale, the idea of air as a smooth fluid breaks. It becomes a swarm of particles. Checkpoint 103. The scale of mean free path as a border. This is a practical border in physics. Above the mean free path, you can use fluid equations. Below it, you need kinetic theory. So there is a zoom threshold where your equations change, not because the world changed, but because averages stop working. Checkpoint 104. The scale of crystal defects. Real crystals are not perfect. They have missing atoms, extra atoms, and dislocations. These defects can control large properties, like how a metal bends. So when you zoom in, you can see that the strength of a bridge can depend on missing atoms. That is another mind blow. Large stability can be decided by tiny imperfections. Checkpoint 105. The scale of superconductivity. In some materials, at low temperatures, electrons pair up and flow without resistance. This is superconductivity. The key idea is that large-scale behavior can be a collective quantum state. Millions of electrons act as one coherent system. So quantum physics is not only small. Under the right conditions, it can become macroscopic. Checkpoint 106. The scale of zero-point motion. Even at absolute zero, quantum systems can still have motion. This is called zero-point energy. A particle in a bound state cannot have exactly zero kinetic energy because of uncertainty. So the idea of perfect stillness is not always allowed. Checkpoint 107. The speed of electrons in heavy atoms. In heavy atoms, the inner electrons can move at speeds that require relativity to describe accurately. This changes chemistry. It helps explain why gold is yellow and mercury is liquid at room temperature. So even the color of a metal can trace back to relativistic quantum behavior. Checkpoint 108. The scale of the proton as a dynamic object. A proton is not a static bag. If you measure its internal structure at different energies, you see different distributions of quarks and gluons. At higher energies, you effectively see more partons, more constituents. So the picture depends on the zoom. Checkpoint 109. The scale where empty space carries energy. Quantum fields have energy even in their ground state. In cosmology, there is a mysterious thing called dark energy, which acts like a constant energy density of space. We do not fully understand it, but it suggests that empty space at the largest scales has an effect. This is another kind of zoom paradox. Small-scale vacuum fluctuations and large-scale cosmic acceleration may be linked, but the connection is not solved. Checkpoint 110. The smallest name and the honest finish. We can name electrons, quarks, photons, gluons, neutrinos, and more. We can name the Planck length and Planck time. We can name the Standard Model and general relativity. But when you ask what happens if you keep zooming forever, the honest documentary answer is that we do not know. We know that our language changes. We know that our tools become violent. We know that our theories stop agreeing. So the final checkpoint is not a thing. It is a limit of description. That is the end of this zoom. Checkpoint 111. The scale of information. As you zoom, the word information begins to show up in physics. A black hole, for example, has an entropy proportional to the area of its horizon, not its volume. This suggests a limit on how much information can fit in a region of space. It hints that reality may store information on surfaces not in the way we expect. This is sometimes called the holographic principle. Checkpoint 112. The holographic idea as a zoom surprise. In everyday life, you think of an object as a volume, but in some deep theories, the true degrees of freedom might live on a boundary. If that is true, then zooming in forever might not reveal smaller objects inside. It might reveal that inside is an emergent idea. Checkpoint 113. The scale of quantum entanglement. Entanglement is a correlation between quantum systems that cannot be explained by classical shared variables. It is real. It has been measured. At small scales, entanglement can link particles across distance. At larger scales, entanglement patterns may be tied to the geometry of space itself in some theories. So the weave of reality could be correlation. Checkpoint 114. The speed of cause and the rule of no signaling. Entanglement does not let you send information faster than light. That is important. The correlations are instant in a mathematical sense, but they cannot be used as a communication channel. So the speed limit remains. Checkpoint 115. The scale of the neutrino. Neutrinos pass through Earth by the trillions each second. They rarely interact. They have tiny masses. They show that matter has layers that do not touch us often. So the zoom does not only go inward, it goes sideways into hidden sectors. Checkpoint 116. Dark matter as a missing layer. Galaxies rotate in a way that suggests there is more mass than we can see. That missing mass is called dark matter. We do not know what particle it is made of. If dark matter is a particle, it could be part of the zoom story as an unseen checkpoint. It could be a stable particle that barely interacts with ordinary matter. Checkpoint 117. The scale of the weak force range. The weak force acts over extremely short distances. It is responsible for radioactive decay. It changes neutrons into protons and vice versa. Its short range is related to the mass of the W and Z bosons. So range is another zoom concept. Forces have effective distances. Checkpoint 118. Radioactivity as an internal clock. A radioactive nucleus can wait, then decay. The exact moment is unpredictable. Only the probability over time is known. So deep inside matter, there are clocks that tick randomly. That randomness is not ignorance. It appears to be fundamental. Checkpoint 119. The scale of the photon as a mediator. Photons are not only light, they are the carriers of the electromagnetic force. So when two electrons repel, their repulsion is described in quantum theory as an exchange of virtual photons. This is not a little ball being thrown. It is a term in an equation that correctly predicts forces. Checkpoint 120. The scale of the gluon as confinement. Gluons carry the strong force. They also carry color charge, which means they interact with each other. This self-interaction is part of why confinement happens. So the strong force is not just strong, it is self-coupled. Checkpoint 121. The strange emptiness of the atom again. If you take seriously how much empty space exists inside atoms, you can do a simple thought. If you removed the empty space between nuclei and electrons, and only kept nuclei packed together, the size of all matter on Earth would shrink dramatically. This is not a practical compression, but it shows that most of what you touch is empty space, stabilized by forces. Checkpoint 122. the scale of pressure inside stars. In the core of the Sun, pressure is immense. Temperatures reach around 15 million Kelvin. Nuclei move fast enough to occasionally overcome their electric repulsion and fuse. Quantum tunneling helps. So even stars use quantum rules to burn. Checkpoint 123. Quantum tunneling as a zoom effect. Tunneling is a behavior where a particle crosses a barrier it does not have enough classical energy to cross. It happens because particles have wave properties. It is why fusion can happen in stars at temperatures lower than a classical calculation would require. It is also why some radioactive decays occur. So zooming in reveals that barriers are not absolute. Checkpoint 124. The last step as a question, not a picture. If you ask what you see at the smallest possible scale, you may not see a thing. You may see a rule. You may see a constraint. You may see that the act of asking for a picture is the wrong request. Checkpoint 125. The closing statement. We started with a table and ended with a boundary. We did not reach a final grain of reality. We reached the frontier where names stop being reliable. That frontier is the smallest honest checkpoint we can offer today. Checkpoint 126. A practical warning about the word forever. In language, forever sounds like a straight line. In physics, forever is often blocked by limits. Some limits are technological, some are fundamental. For zooming in, the fundamental limits are tied to energy, uncertainty, and gravity. Checkpoint 127. Why you cannot build an infinite microscope. To resolve a distance d, you need a probe with wavelength comparable to d. Shorter wavelength means higher momentum. Higher momentum means higher energy. If you keep pushing this, you eventually concentrate enough energy into a tiny region that gravity cannot be ignored. At some point, the energy required to probe the region could form a black hole, so the universe may protect its smallest scales by hiding them behind horizons. Checkpoint 128. The idea of smallest may be a category error. Even if there is a smallest meaningful length, it does not have to mean there is a smallest object. It could mean that distances cannot be operationally defined below that scale. It could mean that space-time has quantum uncertainty. It could mean that the geometry itself becomes the variable, not the stage. So the final limit might be about measurement, not about beads. Checkpoint 129. The simplest takeaway. If you remember one thing from this journey, it can be this. Matter is mostly empty space. The solidity of objects is fields and quantum rules. Heat is motion. Chemistry is electron geometry. Nuclei are a different universe of energy. Protons are storms of fields. And the smallest named border in modern physics is the Planck scale, where quantum theory and gravity both matter, and we do not yet have a single tested map. Checkpoint 130. Ending on a stable sentence. Zooming in forever does not end with a tiny marble. It ends with a question about the structure of reality and the limits of observation. That is why the idea stays in the mind, because it is not only a zoom, it is a staircase of rule changes. Checkpoint 131. A short recap of the zoom ladder. From 1 meter down to 1 millimeter, the world is about surfaces and texture. From a millimeter down to a micrometer, the world is about fluids, stickiness, and cells. From a micrometer down to a nanometer, the world becomes molecules and machines. From a nanometer down to an angstrom, the world becomes atoms and electron clouds. From an angstrom down to a femtometer, the world becomes nuclei. From a femtometer down further, the world becomes quarks, gluons, and fields. Then the map ends at the Planck boundary. Checkpoint 132. Why this ladder is not only for science. This ladder changes how you see ordinary objects. A piece of metal is not only metal, it is a lattice with defects. A piece of glass is not only smooth, it is a frozen, disordered structure. A warm cup is not only warm, it is a cloud of vibrations. And the air in a room is not empty, it is a fast swarm of collisions. Checkpoint 133. One last mind blow. If you could truly zoom in forever and still keep the system intact, you would not just learn new facts. You would learn that the categories you grew up with, like solid, empty, object, and motion, are scale dependent. At one scale, they are useful. At another, they are misleading. That is the deepest change this journey offers. Checkpoint 134. The smallest scale we can name without pretending. We can name the Planck length and Planck time because they come from constants we have measured. We can name them because they mark the point where our current theories are expected to collide. But naming is not the same as seeing. We have not observed a grain of space-time. We have not measured a smallest unit. What we have is a warning label printed by our equations. That label says, below this, do not trust the picture you are using. Checkpoint 135. Final close. So the forever zoom ends not with a last object, but with a last reliable sentence. The universe has layers. Those layers can be described. And the smallest name boundary we can offer today is where quantum physics and gravity must become one story. Checkpoint 136. A last grounding detail. Even if the smallest scale is hidden, the journey down to atoms and nuclei is not speculative. It is built into chemistry, electronics, medicine, and energy. Every phone depends on electrons in solids. Every MRI depends on nuclear behavior. Every star depends on fusion. So this Zoom story is not a fantasy. Most of it is already in your life. Only the final steps are unknown. That contrast is part of what makes the question so sharp. Checkpoint 137. The final picture in one line. A solid world built from empty space, held by fields, driven by motion, described by probabilities, and ending at a boundary where our best maps still disagree today. This was a quiet archive story, where the story ends, sleep begins,